Hello, everyone, and welcome to our third session on MicroPipe. This week, we're going to be talking about sizing refrigeration pipework for maximum energy efficiency. And this is what's key to our industry today, is figuring out how to make and design the most efficient systems for our customers to reduce power consumption, reduce their costs. And I know I'm going to learn a lot today. James, welcome. How you doing, brother?
I'm good, thank you, Trevor, and thank you to everybody who's taken the time to join, whether or not it's morning, afternoon, or evening. Welcome, everybody. Hopefully, the session today will be quite interesting. I've been looking forward to this one in the UK anyway, but I think it's not just restricted to us out in Europe. The cost of energy is climbing and climbing and climbing, and every last little bit of every last percentage that we can squeeze out to save our customers energy is so important at the moment. And I'm really looking forward to it, because I've always and generally specified, and again I'm tailoring it to sort of the supermarket sector. General rule of thumb when we size suction line pipework is sized using a penalty of 2 Kelvin here in the UK and in Europe. And MicroPipe will design within a parameter, but it won't necessarily give you maximum efficiency. So I've been tweaking around and I've been reducing suction penalties, and for sure we see a little bit of bigger pipe work. For example, we might go for a main CO2 suction branch of 3/4 up to 7/8, but what we're actually doing is we can actually reduce that penalty down to a Kelvin, and ultimately that reduces the saturation temperature. That results in the compressor having to work that little bit less. For every single percent we can save, that's 4%. And I'm pretty excited by some of the findings myself in preparing for today's session. So I hope those who've taken the time enjoy the session. Afterwards, feel free, contact Trevor, contact myself. If you haven't already got a trial license, do get in touch with us. We can distribute the presentations, we can send you links to watch the pre-recorded videos we've already done, and more importantly, get you set up with a trial with MicroPipe. Yeah. So I guess so that's it in a nutshell for me, Trevor. I mean, I'm just looking forward to getting out there this evening.
Yeah, me too. And I'm excited to learn about this, because I get questions all the time from different customers and technicians and contractors and end users talking about, what are the steps to make my system more efficient? And when you understand the basics and the fundamentals, that's great. But when you can understand at a deeper level on how to help your customer save and reduce energy before they even start, if they're building a new project, this is game changing stuff. So I'm excited. Why don't we get started right off the bat, James?
Okay.
And if anybody has any questions, you can throw it in the chat. If you want to unmute if you have a question, you're more than welcome to as well. And everything looks real good here, James. We're good.
Awesome. I'll just move the bar out of the way. So welcome everybody, mini series demo 3. So just a real quick overview of MicroPipe. It's been around since the early 90s. Conservatively, there's over 30,000 systems operating in the UK, supermarket, convenience store systems, where the pipework has been sized using MicroPipe. So it's proven, great track record. MicroPipe calculates line sizes based upon user-defined parameters. And this is where I'm going to get where it's got really interesting for me, because those parameters are usually set by an end user specification, so supermarket specification. As design engineers, we follow that. With the cost in energy, I mean, we're seeing some hideous costs. So early part of this year, we were paying 15 pence a kilowatt hour. Now it's 22.4 pence. In October, it's going to be 27 pence a kilowatt hour. We know refrigeration systems, they don't come cheap. It's a necessary evil. To extract heat and make things cold, it costs money. So the software itself, what it looks to do, calculate suction lines, liquid lines, discharge lines, liquid drain lines, relief vent lines. And also we can add valves and bends, so we can actually mimic what's going on in practice, in real life, within that system. So unlike other pieces of software, it doesn't just size single line sizes. This is for distributed systems, and we can go all the way up to the biggest system I've ever designed for one customer was 150 circuits. So the software deals with that, no problem at all. Today's presentation, we're just going to focus today. I am going to open the software at some point, but I've got a lot of images to show, to go through, to kind of explain the implication of how to size suction line pipework for maximum efficiency. Continuing on with the theme, what is the aim of the software? It's to save design engineering time rather than working on first principles from charts, from formulas, where human error can come in quite easily when we're talking about multi-circuit systems. The software saves time. So effectively, what is it doing? It's like a jigsaw. So what have we got in the middle? What's the heart? The refrigeration rack. What we're cooling? Display cases or cold room coolers. And where's that rack going? For sure, we might have a packaged unit which has a rack and onboard condenser, but effectively the software can size between rack and the condenser or gas cooler. So just going a little bit, I've only got a couple of wordy slides this evening. So MicroPipe works on the premise of user-defined parameters, generally specified by the end user. Typically, here in the UK, we look at an overall total suction line loss, which encompasses all the evaporators to the suction inlet of 2 Kelvin. So that line is defined as from the fixtures to the compressor suction header. MicroPipe, we can also set the penalty lower or higher. I'm going to show an example today of what the implication is of what efficiency looks like with having a 2K line loss specified, a 1K. Having a 1K, we're reducing loss in the system. Effectively, I'm sure anyone familiar with the design process will appreciate there's going to be a slightly bigger size on your suction lines within a system. That's going to perhaps cost the end user a little bit more money from day one, but the software then operates below and calculates based upon a single degree pressure loss as opposed to 2. The output of that is an energy saving, and we're talking within the realms of 4%. I'm not going to sit here and say this software is going to save you 50%. It's not, but it's quite incredible when you layer in those costs of efficiency. So this presentation and demo is all about promoting energy efficiency. That's what we're going to demonstrate today.
So James, have you ever been on any job site where you've seen specifically high penalties due to poor design and the difference after it's been fixed or repaired? Have you ever been involved in any job like that?
Hell yeah, Trevor. Yeah. And the implication there is, so if you're a design engineer and you've selected your compressors, you've selected your rack, but if you've undersized that suction line pipework, you're going to have high velocities, lots of losses in the system. General circumstances, unless you're looking at the energy meters and seeing what power's being pulled by that system, it will work. But we're in the summer now. We had a real hot spell in the UK 2 weeks ago, just like you've got now, Trevor, in Canada. The implication of if the system suction line has been designed out of kilter and we've got 3-4K line loss, that's got to be compensated for somewhere. That starts to get compensated for at the rack. And when that system's on high demand, and we're talking about multiple fixtures within that system, all calling for duty, maximum duty, because it's 35, 40 degrees outside, the cabinets, everything's working hard, that's when the system starts to struggle because the compressors are trying to work harder and pulling to a lower temperature, which inadvertently is putting more stress strain and importantly, and using more energy within the system. So So it does happen. I have seen it, but I'll be honest, Trevor, I mean, in the vast instances here within the UK, issues like that are few and far between because the software is applied by the majority of designers who are involved with designing pipework systems for supermarkets.
Yeah. Well, I know I was talking to a manufacturer about 3 or 4 weeks ago. Well, maybe it's longer than that now. Time goes by so quick. Maybe it was 6 weeks ago. But he was like, he got a call from a contractor who bought the equipment, installed it, and they were like, "Ah, I'm not getting any oil back to my compressors. I keep going off on oil issues." And they were asking, "Did you check your superheat? Did you check your pressures? Oh, everything's good, but the oil's not coming back." And so he asked them, "Can you go check what's the pressure at the outlet of the evaporator? What's the pressure at the inlet of the compressor?" And there was a 12 psi drop.
Mm-hmm.
So no wonder he wasn't getting the oil back. So this is an issue with the sizing of the suction line.
And that, Trevor, actually, you raise a good point, and that goes back to last week's session when we discussed sizing suction lines for good effective oil return. We see that in the UK as well, because the software, even using the software, it's as good as what the user parameters goes in at. But that for me is more of a thing than those couple of days real hot weather where a piece of plant could struggle if the pipe works inappropriately sized. We're touching on energy here. There'll always be a big energy impact there. But the thing that I would always look for is, are we going to get that oil return? You know, and that's the first thing. So if I check anybody's design, the first thing I will do, I'll go to those riser pipe works, and I will see what is the minimum oil return duty that's been set for that riser. Because if it's too high in low ambient conditions, we might not get that oil back, especially in synthetic refrigeration systems. CO2, and I've based the calculations this evening on CO2, although as a fluid, a little bit less efficient than synthetic refrigerants. One of the great things about it is because it is relatively high pressure, you don't get the volume of oil problems on these systems, not within the pipework anyway. You know, I can't pass comment because I have seen oil problems at the rack itself, but that's generally just the oil management setup at the compressors, but within the pipework itself. So just moving on a little bit, I think now just to talk about the traditional method of sizing pipework. So sizing from charts specific to a refrigerant, looking at tons of refrigerant, looking at temperatures, looking at pressures. When you're looking at single lines, sure, you know, it's not that big a task to size a piece of pipework. Then you can add complications if you've got a number of bends in and you add some valves in, because obviously things are, you know, it's moving from an internal surface of copper and could conceivably, you know, it's going to get turbulent when it passes through that valve. So that's something else that the software compensates for. And obviously Trevor, with refrigeration systems being really dynamic, the software compensates for that, where we talk about a lot of problems that can happen, you know, we will always look as a designer to design for maximum design conditions, i.e. high ambient, high condensing conditions. But something that we can often overlook, and the biggest problem with specifically suction line pipework, as I've said, it's that, and as you've mentioned, it's oil return. And it's oil return in those low conditions where you've only got a percentage of your fixtures which are requiring cooling at any one time. You'll always have some on a defrost, just some that are satisfied and holding temperature. The solenoid valve, the expansion valve, it's not really doing anything if the temperature is satisfied.
Yeah.
So the last part of so we've gone through the benefits of, you know, a standard is designing for a 2K line loss. You know, I'm going to show what happens when we select for 1K, because I think it's pretty awesome in terms of rising energy costs. Then we're going to look at 3K. You know, I don't think I've ever come across somebody who's used the software to select 3K as a line penalty. There's nothing to stop somebody from doing that. And it's certainly not saying the system will work, because ultimately as long as there's enough capacity to operate at the rack, at those compressors at that lower temperature, that's okay. But I'm going to show how a higher penalty can impact energy and performance, demonstrated today. So moving on, what I've sketched out here. So, and I will say this to anybody who's got MicroPipe at the moment, I can send these calculations. I've already preset them. So I'm effectively showing a real small system here with number of fixtures, and then so the isometric, the schematic matches up with the plan, and we've got circuit number 25 here, which is effectively the final service route before it goes into the compressor rack header. So that's the big line, so we can see it's picking up the duty from all other services. So I want to concentrate on that, because that is the key suction line. That is the main branch of the system, which I'm going to show the implication. So moving on, hopefully everyone can see this. So on the left-hand side, we have the input parameter of White Rose software. And everybody, I will open the software shortly once I've gone through, so you can see it in action. So design inputs assuming 5 degrees, -5 evaporating, suction superheat of 10, maximum liquid at 5, minimum liquid -2. This is for a CO2 system, and maximum penalty of 2 Kelvin, which is pretty much typical. To the right-hand side, if we look to the right-hand side of the screen, where we've got the black boxes end network, and underneath we have 25 of 25. That's effectively just saying that that's the final circuit, the one that I'd circled on the previous slide. So the software is saying it's sizing for 7/8. So I come down, look at the velocity, 11 meters per second. Hey, I'm good with that. Out of that 2 Kelvin penalty, it's used 1.74. So you add your 1.74 to your evaporating temperature, you have a saturation temperature of -6.74. So if you're selecting a compressor for -7, this is absolutely fine. The system's going to be designed, it's going to be designed well. So as an overview, just to reiterate, so suction line penalty of 2K in this instance gives a maximum penalty of 1.74K, equating overall, taking into account the evaporating temperature, -6.74 Celsius as the saturation temperature. I want to flick on to the next slide. This here, I've set the penalty. So every other design parameter still the same, -5 evaporating, 10 Kelvin suction superheat, 5 degrees, maximum liquid, -2, minimum liquid, maximum penalty, 3 Kelvin, a Kelvin more. If we go to the right-hand side, MicroPipe is going to pick, it's going to select this pipe size based upon those parameters. That's really important to remember, the parameters that are fixed there on the left-hand side. What we've got at the moment here is it's selected 3/4 line size. Got a horizontal line velocity of 15.28 meters per second. That's quite a high velocity. I'm not saying that system's not going to work. It's going to work, but it goes against better practice where we might aim for a per meter basis of 10 meters per second, 11 meters per second. Crucially, the penalty in circuit 25, the main suction branch, is 2.6 Kelvin. So it's not quite up at 3 Kelvin, but when we add that 2.6 to the evaporating temperature, we have a saturation temperature of -7.6. So if we just go back up, before we were at -6.74 when it hits the compressor, now we're at -7.6. So as you can see, I think I've done a little bit of modeling away from MicroPipe to show the implications of running a system at a slightly lower condition and its impact in terms of energy and efficiency. So going down to the third example, again, left-hand side of the screen, all the design detailed user parameters. So we're still -5 evaporating, 10 Kelvin superheat, 5 degrees maximum, -2 degrees minimum liquid temperature. This time with a penalty of 1 Kelvin. Moving to the right-hand side, we can see what the software's done now. It's automatically selected against that lower penalty, and it's selected a size of 1 1/8 inch. Come down, we're getting a nice low velocity of 6.55 meters per second. Ultimately, we've got better control. We haven't got pipework whistling. We haven't got to concern ourselves about the turbulence, the losses that are encountered through bends. And of that 1 Kelvin that I've set, because it knows it can't exceed that 1 Kelvin, it's looking for its most efficient option, which is 1 1/8 inch. The maximum penalty it's induced is 0.85 K. So we add the 0.85 K to the evaporating temperature at -5, gives us -5.85. That's what the compressor is going to see. So instead of the compressor may very well be selected to deal with a saturated suction temperature of -7, but if we can give it less, it's got less work to do.
So James, you just showed 3 examples with different sized suction lines. Okay,
Absolutely.
so now we're going with say a lower maximum penalty. The suction line gets bigger.
Absolutely.
So that adds more costs to the job, for example.
Yes. Yeah.
So how can we tell or get the offset of what would the difference between now buying more material to that energy efficiency side? Is there a calculation you can do? Is that how would you do that? Is there ways to do that?
Well, from my perspective, Trevor, having costed jobs up, I know without showing, but you raise a good point. And I think actually, before we distribute these slides, let me put a table in, because I'll show, I will cost this system against a schedule of rates as per 2 Kelvin, as per 3 Kelvin, and as per 1 Kelvin line drop. They're all different. Obviously, we're looking at, there's going to be slightly different sizes, especially when we're designing for efficiency. We are going to see a slight cost uplift. But where I get really excited, Trevor, 12 months ago, I would have actually said, the most efficient a system can be, that's great, but just remember about the capital outlay. But in the UK, we're talking by October, the cost of energy has almost doubled.
Crazy.
It's a whole different pendulum swing at that time, Trevor, especially when you factor in the savings over the lifetime, which I've assumed in this instance to be 15 years. And this is exactly what I'm going to be showing everybody on the chart on the following slide. So looking at the bottom, we've got three graphs. We've got 1 graph, 3 lines. 2 Kelvin penalty. We're looking at an annual running cost in this particular system. This is modeled, this is using calculation, this is using my experience. Over the course of a year, this running cost is going to be £28,174. If we run with a 3 Kelvin penalty, the cost's going to go up because we've got to lower, the system's got to work harder, £29,301. When we reduce the penalty to a Kelvin, our actual running cost goes down to £27,047. So it's effectively over £1,000 cheaper per year by reducing your suction line based upon the 22.4 pence. We already know in the UK we're going to be jumping up to 27 pence very shortly in October. That just extrapolates and expands that saving so it's even bigger. You're absolutely right, Trevor, what you've said on the page before, and that's why I want to add another slide in.
No, that's perfect. I didn't even know the slide was here. So And
Hey,
what I noticed too, like that 7/8 line, I think that was the standard line. Just say it was, I can't remember the footage or how many feet it was or the distance in meters, but going from a 7/8 to a inch and one, that cost difference is not going to be that like over a
no,
thousand pounds, you know.
it's
So
not,
it might be
Trevor.
400 or 500 pounds it costs extra for that 1 inch and 1/8, but definitely not that. And then year over year compounding, like
Well, this is
that's
where the right-hand side of the table above the graph, I've assumed a 50, and I think 15-year run for a plant system is good. If it's well maintained, I don't see why a plant system shouldn't last that long. But, you know, if it's 10 years, I deal with one customer in the UK whose expectancy of a system is 20 years. So we know that we can get life out of the systems as long as there's investment made by the end user themselves, and that investment ultimately relies on having service technicians having the ability to spend more time on their sites rather than just being reactive.
yeah.
But over 15 years, when we compare, and let's just park the 3 Kelvin, because in some respects, I don't think anybody would willingly, especially using the software, would design based upon an overall line loss of 3K. But when we look at the difference between over 15 years of a 2K penalty over a 1K, we're talking £17,000. And initially that's over, as you say, Trevor, that main suction branch. There may be some implications further down the system as well, where some other sizes might be slightly larger. But you're not telling me on such a small system that jumping up from 7/8 to an inch and one, and the difference between those two sizes is going to have such an impact. As you rightly said, we're probably looking more in the £500-600 region.
Yeah. And this is just real education for the customer and education for ourselves. And when you're talking to your customer, this is what they need to understand. Because at the end of the day, a lot of the time the customers don't know this stuff.
Trevor, it's education for me. When we set this program up and I'm really pleased we've got some great attendees joining us this evening. As I've prepared for this, I always knew, I've been a designer for a long time. And, you know, you always try to raise your suction condition, you know, have a higher evaporating temperature, all that good stuff that we do as designers. But when we're talking that energy, you know, it started creeping up sort of 18 months ago. But when I had one customer who were paying 12 pence kilowatt hour, then others 15 pence kilowatt hour, you kind of thought to yourself, well, is there really any need to, you know, is by tightening up that penalty, what is the customer actually going to gain? In preparing for this evening, I was absolutely blown away by the fact that, you know, we're not talking huge differences. You know, don't get me wrong, we're looking at, you know, between a reduced and standard penalty, you know, about £1,000 a year, well, £1,100. Before the cost in energy increase in the UK, we might have been £400, you know, in terms of benefit. And at that case, at that stage, you think, well, if your customer's prioritising installation work and the number of projects that they're going to take on, they might not want to listen to the possibilities attached to using slightly larger refrigeration suction line pipework to squeeze a little bit of energy and make systems more efficient. But now so I've educated myself in terms of this is really, really important. And I've already sent this presentation deck off to some people who I work with in the UK sector, just to emphasize, look at this, you know, this is quite surprising. It's a positive surprise in some respects, because we're going to be able to help our customers reduce their energy consumption.
Yeah. And it's not like energy is going to go down. Energy is just
Well,
continue to keep going up there. Nothing like that goes down.
there's been an argument, Trevor, recently in the UK. I actually, when I prepared this, we've got a relatively an independent shopkeeper who's got a convenience store in the village where I am. I thought, I'm going to go see Dell. So this guy's got a number of shops, and I queued up and I said, look, I want to know how much you pay for your electricity. And he started laughing. He said, and smaller loads than what we're dealing with here. This is a real small store. He says, well, I fixed. He said, I spend £17,000 a year. He said, but I've managed to fix 18 months ago at 13 pence. And I said, what's going to happen when you're off that fixed rate? He says, well, if energy prices don't go down, I might have to actually close my shop, because the reality is I could then be paying £35,000 a year, and that's £1,500 nearly a month that he's got to find from somewhere. You can't increase your cost by that much. People will stop shopping with you. It's a real difficult time. So, it then asks questions. Well, what can we do? What should we be doing? The obvious one away from pipe design is putting doors on chilled refrigerators. That's a given. But even then, we can still lend ourselves to exactly the same scenario that we have here. We can still tighten things up. We can still work within a lower penalty band. So just moving. So this here, this is where we get. This is where it gets really, really interesting. So if I look at the largest convenience store operator in the UK, the Co-op, they have 3,000 stores. So looking at the impact at single store, just to reiterate what we've been through, when you compare a 2 Kelvin with a 3 Kelvin difference, potentially save £1,100 a year. When you compare the reduced 1 Kelvin versus 3 Kelvin, you're talking £2,250 a year. And you look at those 15-year life savings, £17,000 or £34,000. When you look at that chart below, this is where it gets absolutely staggering. When you multiply this out by 3,000, look at those savings. And let's just concentrate on the standard versus high, the smaller figure. It's £3.38 million. You multiply that out over 15 years, which is a long time, and each 3,000 stores, sure. And I'm not saying, some systems will already be efficient. So I'm pushing the impact of it up for a positive spin. But we're talking serious money. We're talking millions and tens of millions of pounds if we extrapolate just doing something like this through the design phase before we construct a refrigeration system.
Yeah, that's amazing.
So really, really interesting. So I think, Trevor, I've just noticed there's a couple of chats in, whether or not we look at the chats, and then I'd actually just like to go through the software to show people,
let's do that
in action.
Yeah, so the first question here that you can probably show, does the software also recommend the right wall thickness to meet PED and PESR requirements?
Absolutely does. Yes, it does. So what it will do is it will automatically, it's set very much for the UK at the moment, but when we expand, so we're working to the applicable British standard, so it will give you the correct gauge of pipework based upon that specific refrigerant. For CO2, we can even go one better. Standard refrigeration grade copper pipework can be appropriate, especially smaller sizes, for higher pressures. MicroPipe will actually force, it won't allow you to, it won't select anything of a larger diameter pipework if the gauge and wall thickness is too thin. So you can actually select K65, which is the copper iron alloy, which, are you aware of that, Trevor? Have you come across K65?
Yeah, I was on a site last week or 2 weeks ago, transcritical booster site, and there was some K on there, K65 on there. But here in Canada, there's regulations where you can't use K65 on the high side because of our UL limit. So you still have to go with stainless steel. Well, that's what we do use here, stainless steel, because it got to be 5 times the burst pressure rate, and K65 is not 5 times.
Yeah. That's you've taught me something there, Trevor. That's safety to a whole new level, because I consider what we do in the UK being, we're risk adverse, but that's really taking it to a whole new level.
Yeah, always learning.
I think that's a good. I've just seen a chat pop up from Kathleen. Why K65 has become, when stainless steel is cheaper and viable and much cheaper. That's a great question, Kathleen. The reality is, though, when you start with copper, you're brazing that pipework. The labour associated with brazing a system is much more cost effective than bringing a coded welder in.
Yeah.
So I think Alexander there, it's easier to work with. You're not looking, I'm not decrying the skill set of an installer putting copper pipe work in, far from it. But generally speaking, if you go to a steel-based system, the installation time takes longer to get those welds rather than a braze.
Yeah.
I'm just looking. I'm just reading another point from Alexander, actually. It would be interesting to do the calculation with annual energy price increase and inputted rate of interest. Absolutely. Because effectively, I'm just going on what we know in the UK. But when we look at the interest, yeah, absolutely. It could actually compound. It would compound year on year if we look at, say, an interest hike of sort of 3%, just standard interest rate rise. So, yeah, good point, Alexander.
So, James, I worked on many projects when I worked at the manufacturer, my previous role with Emerson, and I've done tons of energy audits. I've helped customers save tens of thousands of dollars by doing efficiency upgrades for low condensing is one, for an example. So you're taking your condensing pressure and you're reducing it as low as you can to make the system run effectively. So you're getting that lower compression ratio, less work, more capacity, less power. How would that affect the suction, or would it have any effect? So just say I go with that 1K penalty, so it's a bigger line, a bigger suction line, but now I start to reduce my condensing pressure. Is there any effects there? Could I have any issues with the flow or velocity because of it? Because now I'm going from running at 225 psi, just for an example, and now I'm running at 145 psi.
To be honest, we're looking, Trevor, on the other side of the compressor. Yep. At that stage, it's high pressure, high temperature anyway, yep. Even though we've run it a little bit more efficiently. So it's not really going to have that kind of impact. And I think actually but it is a good question, because there's only so far you can take your condensing, especially in low ambient conditions. I think this is another plus. There's a lot of reservedness and negativity in some instances, even by me, with CO2. But one of the other advantages with using CO2 as a refrigerant is its higher pressure actually supports what we're looking to attain within a cycle.
Yeah. So yeah, let's share your screen with the software.
Awesome. I'll just launch the software and then I'll save it. And I think I forget just before I do that. So yeah, Kathleen's question regarding wall thickness, real good. So I'll actually be able to take you around into the parts of the software.
Okay, you're sharing now.
Awesome. So I'll just take everybody through what you were just seeing on the screen there. So I've set, this is exactly the system. So it's the connected load. This is the 25th circuit. This is the Incheon one that we've calculated. 6.55 meters per second, and this low saturation temperature, or this higher saturation temperature. So just to give everyone a taster of the system. So all I'm going to do here is I'm just there simply increasing the penalty to 2 Kelvin, just hitting this key here. So you can see it's reduced from inch and 1 to 7/8, which is a positive for the construction phase and the costs. Slightly higher velocity within its 2 Kelvin limit. So 1.74 added to that -5, we've got a saturation temperature within tolerance. If we select 3 Kelvin, go back to the suction tab, run it again. What we've got now, to try to so it knows it wants to target, and it can go up to 3 Kelvin. It's always looking to look at things from a holistic perspective. So it's dropped the size down to 3/4. Got quite a high velocity in what is a horizontal line. It's absorbed 2.6 of the 3K. And instead of what we were actually aiming for, of a -7 saturated suction temperature, which is what in this instance a compressor would have been selected on, we're at -7.6. So due to the small diameter pipe work, we've got more of a loss, more of a penalty, and that's going to impact the efficiency of the system. So just moving somewhat on to refrigerant and tube. So what we see here is, and sort of specifically for Catalin, what we look at is, first thing we do when we launch the software, you can see here I've got the software selected for carbon dioxide. So I can actually, from here, it's a suction line. I've selected here K65, but I can select I want copper to 12735. So I'm going to close that down, apply settings, and it's fine. It knows, and when you printed out that calculation, what it does, it groups up all the 3/8, all the 1/2 inch, all the 5/8, all 3/4, all 7/8, which is the biggest size in the system, and it'll total up the meterage, and there it will tell you the gauge of copper pipe work to order. So whether or not it's 20 gauge, 18 gauge, 16 gauge, it will give you the most cost-effective option. What's really cool about the system, and I've actually run this evening I'm going to take that back down to 2 Kelvin. I'm just going to run that through again. I've set this up as SI. Let me just see here. So I'll just move this bar out of the way. So I'm at suction. I want to convert to SI. I want to convert to imperial. So you can see what it's done there on the design entries. It's automatically just taken from my metric. So we're looking at 23 Fahrenheit, which is -5 degrees Celsius. It's changed the suction superheat to 18K, maximum liquid at 41, minimum 28.4. But you can see it's auto translated there. So we go to the suction tab, instead of reading in kilowatts, we're now reading in British thermal units. So as you can see, it doesn't make a bit of difference to the diameter pipe work, but the outputs for a lot of the attendees this evening, you might be looking at things that are a little bit more familiar now, in terms of we're looking at losses in PSI, we're looking at velocities in feet per meter rather than meter per second. And again, reading in Fahrenheit. So the software is pretty, it's pretty good. It looks quite dated. We're going through a period of modernization shortly, which is going to be really cool because we're going to have so many more features added. But effectively, this is this is a software from a suction line perspective. So we can go back, set the suction. In fact, I'll change them all. User error. User error. I've changed it, so it thinks it's changed. It won't let me change it back.
Awesome.
So yeah, I've managed to screw my software.
So not the first time, but you,
Yeah,
you get to
no,
see
no,
the
not at
point
all.
that it's very important to reduce that penalty as best as possible. And so when you did it before using the software, James, you would have tried to figure out this penalty through charts. Is that correct?
Yeah, absolutely.
And I can just see, because now this is a whole integrated software where you go from your circuit one through all your network, from all your terminations and terminals, and you can easily change that. That's amazing, right? That because you can go to your customer and show them the differences very quickly, print off these documents, and actually send them to them so they have like a copy of it, like proof of that design. And then if any changes need to be made along the way, that can go right into their folder, and then you can pull that up quickly instead of, I'm sure before you probably had filing cabinets of charting and of designs.
Yeah. Well, Trevor, when I joined the industry, it was 20 years ago, and I'd served a mechanical apprenticeship and worked as a manufacturing engineer and a service technician for a couple of years. Joined the industry, and MicroPipe was a thing by then in the UK in 2002. So I was shown the software, how to use it. To your point, I had a colleague. I worked under him for a time, so he's long retired now, but he wouldn't use the software. And you should have seen his design files for every single project, Trevor. They were just, and he wouldn't even use Excel to do calculations. You know, it was all longhand. It was all reading off charts, actually plotting it down, writing down in pencil on paper, so he could rub out any mistakes or any changes. And a design for him to design a store could take him up to a week if it was a big store. If we're talking a 400 kilowatt medium temperature load totally and a 70 kilowatt low temperature load, where using the software, it takes nowhere near as long. It's a fraction of the time. You'll do a full design within a day. And what I mean by that is doing all your load balancing to select the compressors, to select the plant, sketch out your isometric, your service route, number it all up, put all the details on, and then run it through the software. So I hazard a guess, the software probably very conservatively 75%, but probably more 85, 90% of design time that's associated with sizing pipework can be reduced using the software.
Awesome. So is it so the main thing for design is have the correct suction line size for the maximum efficiency of a system? Is that the statement correct?
Yeah, well, to be honest, Trevor, you design through your parameters. So your parameters will guide what you should do. So if we're looking in the UK at 2 Kelvin suction line loss or penalty, that's the aim. But I think what's come to my mind now is actually, if we start to reduce those penalties further, what we can ultimately end up with, the ability to run a system more energy efficiently, which, especially here in the UK, the name of the game now is efficiency.
That's amazing. That is amazing. I love it. And just understanding this is definitely going to help me help my customers now, because I've not really understand the concept of line sizing can make your system more efficient, because I've I understood that it can make a lot of issues with oil because I'm always thinking on the technical side, but
Mhm.
now understanding that it can help increase the efficiency of the system is just awesome for me to understand. I love it.
I'm gonna, Trevor, if you don't mind, I'm gonna hit it over some. Great, Kathleen. I'm glad you've enjoyed, the demo. As I mainly use a mix of SI and Imperial, but smart function. In the actual market, it would be impossible to secure any jobs with pen and paper. Do you know something? This is absolutely right. And going back into the 90s, when the software was first developed, the traction in the UK was quite slow. So my mentor, Ian, who designed the software, absolutely the very best technical design refrigeration specialist the industry is known in the UK. This guy was something else. There weren't that many supermarkets back then. They became a thing sort of from the mid late 90s, the explosion where Tesco, Asda, Sainsbury, Morrison's, they all started to grow their estates. So back in the early days, I remember joining the Epta Group in 2002, and Morrison's had around 90 stores throughout the UK. Now they've got nearly 500. And so, to the point of my old contracts manager who I used to work with, there was a real good design engineer, he was a good technical engineer, no two ways about it. He was good, but he did everything on pen and paper. I think people had more time back then. Now we don't, and although supermarkets are kind of saturated in the UK, we do have a couple of Aldi and Lidl who are growing all the time and are opening more and more stores. But we've got all these stores now within the UK, and unfortunately, separate conversation, but it's impacted the high street a lot by having so many sort of supermarkets. But they've all been through a mid and a total, and often they're back at a mid and a new total life now. So there's been multiple rip outs in these stores where new cabinets have gone in, or new plants gone in, or new cabinets and plants have gone in. Each iteration, we're generally installing and designing brand new pipework systems, especially when we transition from HFCs to CO2. And even when we're transferring from HFCs to, there's a couple of retailers installing A2L HFO systems. There's anything mildly flammable, we can't put as much refrigerant in the system. So we've actually got less, we've got smaller plant, and we've got smaller distributed pipe systems. So the services are smaller. So we're in a society, especially in the UK, where it's all about volume and getting volume out of the door. But to Kathleen's point, just to reiterate, great point. But a long time, 30 years ago, the supermarket sector for refrigeration isn't what it is now.
Yeah, no, I totally agree with that. It continues to change rapidly. And that's one thing I like about the software, because I talk to a lot of manufacturers and they are just still using a single line sizing software. So they still using software, but they got to do each one individually. So that would take way longer than using a software like this, where you can just continues to put them in, and you can use each terminal and each load, and it would be way faster, because I know I have some of my friends who are comparing this from what they use there to now, and I'm excited to see what the results are, because I know it's going to be a saving time on using this distributed sizing software compared to doing each one individually and going back.
If you do each one, everyone, and I'm not going to criticize what's out there. I think it's great that companies have come up with tools. But the reality is, if you use a tool that's just going to size an individual line, then another one, then another one. What happens when you're joining? You still need to do some intermediate calculations, because when you're joining a header which might be connected to 2 terminals, then it's picking up 2 more terminals. That header's growing and growing. Every time you're adding load to the system, but you're adding losses, you've got bends. A single line sizing software isn't able to do that.
Yeah, And that's what's amazing about it. 'Cause I'm learning so much about the software too, each week, each month, and it just how do I help more people? And I see this consistently. The manufacturers that I work with and I talk with, they're just it takes them long. They're telling me me a while. It could take me a half a day or a day to do a small job. Where I seen on here, we did a small job and you did it in 7 minutes. You do have to understand what you're doing. You have to draw it out. So that does take some time, but it's a dramatic amount of time
Absolutely.
savings. And time is very important and very valuable today for me, right? So
It is for me.
I
Yeah,
appreciate
Trevor,
it.
I've just, if you look at the comment there from Kathleen, just imagine this software integrated with the equipment selections. That isn't, so we talk about the modernization process that we're looking at doing. And I appreciate we're coming up to sort of 8 p.m. where we're gonna call off. But if I can just introduce, so a lot of my work, just let me see. I should be able to find something relatively.
And so, just so I understand the question, maybe the way you are taking it, James, is that having this sizing software, and for example, they could pick an NEPTA case, a Hill case, a Hussman case, or that's what you think, and are there a rack itself, you think, or
Oh
what
yeah,
does?
no, I'm talking about the plant end. I mean, because your Hussman, your Hill Phoenix, etc., they're gonna predeter, they're gonna actually advise you what their duty of their cabinet is. So you automatically know what you're working with. So the MicroPipe, all it needs is a duty,
Hmm.
effectively. So so there, I think I've got the spreadsheet here. So I'm just going to quickly share the screen and what I'm wanting the software to do. So I don't know if everyone can see this. Is my screen shared, Trevor?
Yep. Yeah,
Yeah.
it is.
So effectively, this front sheet's a bit of a master, and I've got engineering, case costs. So a lot of information built in by different system types. So starting off with HFCs, which obviously being phased out, but what I want the software to have the ability to do. So these are my own calculations here, just using, so we can clearly see here, you know, as part of an integrated process, which Kathleen's touched on, which is what I want to introduce to the software, is when I do my energy calculations, I'm working in a range of maximum condensing down to lower condensing, suiting, matching all ambient hours in a year. But effectively, the information I'm grabbing here, this in this example, because I've selected a Copeland compressor, I'm using their select software. Their select software is giving me the power input and the capacity of a compressor at a known condition. So this is where I want to get the software to, as part of its modernization, is to actually be able to model what the energy consumption of a system is going to be, and actually allow users to do a comparison. So they can clearly say they've done a calculation, it's going to be CO2. What would that look like if it was HFC? What would it look like if it was HFO? And I always, in my calculation, I don't know how big, you know, away from the UK people are on total environmental warming impact. So I always mix in with a Chewy calculation as well. So where it's capturing the overall system loads, compressors, ancillaries. So I want the software to actually state what is its carbon output at the end, what's its modeled efficiency based upon, for example, here, if we've got a you know, a leak rate of 5%, you know, what's its impact if we have a 10% leak? I want it to be a fully integrated, more useful tool than just selecting software. So to Kathleen's point, integrated, where I can actually communicate, or if I can't communicate, at least have a database of compressors and components by different fluids and by at different temperatures and at different pressures. So I just thought that was worthwhile sharing.
Awesome. Yeah, no, that's amazing, and it's going to get there. Um, awesome, awesome session, James. I really like these sessions because I'm always learning, and I'm getting better.
Excellent. No,
I'm
I've
consistently
I've
getting
really
better.
enjoyed it. I hope people who've listened, and all I can say, just reach out. Just as always, anybody wants a trial of the software, anyone wants any one-to-one sessions with either you or me, Trevor, or both, as always, we're happy to just reach out.
Awesome. I want to thank everyone for taking the time to hang out with us. And next week, we're going to be diving into how to design the full pipework of a medium-sized convenience store. So we're going to take it and we're going to see how James does it from scratch, building a whole pipework, which
So
I'm
those
excited about.
25 circuits everyone's seen today, I'm going to be building it up from circuit one. So I'm going to be scrapping what I've done, and I'm going to be going from start to finish,
Awesome, James.
including the discharge line as well.
Love it. Love it. I want to thank everyone once again. James, thank you so much. And we'll see you all at the next session.
Yeah. See everyone later. Bye.